studied at a location that related to this pathway, and they showed that they can increase the production of this pathway, dramatically in just like, only in a period of like just like weeks, instead of taking the whole year to optimize the pathway. All right. So those are those kind of research that is going on in synthetic biology, and there's also other aspect that I should mention here, which is the community. All right. It's not just research; we also build the community, and it's kind of interesting because one of the first few founders of the field had the idea that all this technology should be free, at least at the bottom level. So the analogy was that they thought that the technology that is on the top, if somebody's gonna figuring out a way to cure cancer or solve energy problem, okay, those things are patentable. But the basic technology, like the promoter catalog or like the technology to mutagenize the genomes or whatever, those things should be the basic technology that's free. Because you think about computer engineering, right? All these tools are the free tools. Programming language are free. And it's important because all this fancy, not free technology can be built upon, right? So the community, the growing community of synthetic biology try to keep the basic technology free. And this is a good thing for us and also for the world, right? And these are some like all the community that we are part of. This is like the Synthetic Biology Research Center in the US, and it's like some of the foundation that try to create the open source genetic material. Okay, one thing I should mention is the iGEM. So it's International Genetically Engineered Machine Competition. The way the iGEM starts is kind of interesting because it actually started by the professor that I'm working on right now. But it started back in 2003 when he was at MIT. And the dream about, we can engineer like the cell to do anything that we want, the composition that's easy, it has been around for a while. But all those professors and scientists cannot figure out how to do it. Right? But the way that they start, instead of trying to figure out everything and teach the student, they let the student teach them. So basically, they set up a competition. So like, I think that the first competition is like try to build the oscillator or something. And they have two teams of students. This one is just at MIT to compete with each other to build the oscillator. And of course, the first time it failed. They can't even get their DNA by the time that the class is over, right? But they're getting better, coordinating with the gene synthesis company and also like figuring out the technology to refine the process. So 7 or 8 years later, this competition is growing. Right now, it's an international competition. I think like last year, there are like 180 teams competing for like building this tool, this kind of genetic engineered machine from like, I think like all these teams are from like at least 30 to 40 countries. All right. Another nice thing about iGEM, besides the fact that it's a fun competition, is that it's a way to build a community and also the machine that generate all this collection of parts. Because each year, all these teams, they receive the collection of parts from like the registry that I showed you earlier, right? And whatever they build, they have to contribute back to the registry collection. So basically, for each year, you're going to have a growing collection of parts, collection of devices that all these crazy undergraduate students came up with, right? So those are some kind of community that are building. Besides iGEM, there are also other research area that is extend beyond traditional research lab. This guy is one of the postdocs that used to work in the same lab as I am. So he's a sociologist and trying to figure out a way to do the design and different kind of art based on the technology created by synthetic biology. So this project is called synthetic aesthetic. So the beauty of engineering life, right? And the way they thought about it is like, there's some, any kind of new technology, computers or like, like civil engineer, for example, it creates an opportunity for new kind of design, new kind of art, right? So in this project over the past year, so basically they try to have 6 artists and designers and 6 scientists and engineers and try to figure out, maybe they can figure out something cool, something that they can build. for example, like, let me tell you about some different projects. This project here, let me see, human microbe and the smell. So basically, they pair up the artists. Not the artists. They are like the people who work on cheese. I think it's in France, right? And they try to match the study of human microbiome, like different kind of microbe in different part of human body, to the cheese that they make. And they try to figure out the new way to make cheese, for example. And like some of these projects, I think, let's say this one, for example, people try to use the tool that architects normally use to design the building. So if you don't know that, like these days there are tools that allow you to optimize the way you design the building. For example, you want to design like a chamber in the train, for example, right? You can put different parameters in. Let's say, oh, I want it to be this size, and I want it to have 5 windows, and have a good ventilation system, whatever, right? And the program just generates hundreds of different kind of design that the artist can use for. And they pair it up with the plant biologists, the botanists, right? And they try to use this software to study how plants actually optimize its structure. You think about plants, right, the way they evolve. It also needs to optimize something, optimize for light, optimize for whatever. Basically, they try to exchange the technology using the tool that architects use to understand the way the biology works. For example, these are some examples we can talk about that afterwards. And also, there are also some community that is outside the academic lab or the industrial lab. So these are the people that they call themselves a biohacker. So you think about computer, right, or the internet, right? This technology, the way that it starts from not from like the factory, not from the school actually. It starts from the garage, right? It starts from some guys who think like, oh, I can create Facebook, or I can create the Google or whatever, and they work together in the garage, right? And then they build something, and it's become like the groundbreaking technology, right? So these are people who thought that no, over the next decades or two, biology is going to be so easy to engineer that we can do this in the garage, right? So there are clusters of these people all over the world, and near my university, in the Bay Area, in San Francisco, for example, there's one of the huge group called Biohackers, for example. They try to have their own like community labs, have the PCR machines and all those kind of stuff, and so that they can like try to build like the new biotechnology by themselves. And, there's some controversy about like is it going to be clean, is it going to be safe for the environment, such and such. But they're on the process of working toward that. So like it or not, these kind of things are coming up. They are new players in the field, not just us in the academia and the industry. Now, the last few things that I'm going to close this presentation with is, so what are we going to do, right? In terms of like Thailand, right? So I discussed this for like an hour with my advisor, because like I said, like, I'm going to go give talk in Thailand, and we try to figure out what to do. Or if we shouldn't do anything, then that's a good decision too. I mean, if you want to decide that, then we should make that explicit, right? And so we try to think about that. And so here's the suggestion that my advisor has about my question. So he said like this. All right, right now in the world, there are at least 2 big players. There are some in Europe, but these are 2 big players in synthetic biology right now, the US and China. Right? And there are all these different programs that mostly focusing on building the basic foundation of synthetic biology, how to make a better promoters, a better like selection technologies, all those kind of stuff. So these are what the big players do. Right? Now, but there's, for example, like this is like a synthetic biology research center in the US. So they focus on this kind of stuff: how to make a better part, how to make a new oscillator or a new memory, how to build a better strain, for example, or like how to take care of all these like issue about like safety, security, and how we're gonna share this stuff. Those are the foundations that the big players are thinking about. So it's really difficult to compete with the big players. They have a lot of money, power, right? But the big player like this, they also have some weakness that we can fill in, that we can lead them. So most of the applications that they thought about are kind of long-term applications. Thought about curing cancer or like colonize the Mars or something. There's actually a project like that working with NASA to like colonize the Mars with a new microbe or something. There are some kind of things that the big player didn't think about. And so he asked me this question, like, what is the rate limiting step of the software today? And the answer was that figuring out what to make. Right? Because like in the early days, all this technology, all this computer is really expensive, right? So who has the better computer, the fastest one, the better chip, the one who win the game, right? But as the thing getting cheaper and easier, the rate limiting step going to be figuring out a nice application that might not have to be difficult, but something that's simple and elegant that nicely correlate with the technology that's moving forward. Right? So figuring out what to make, focusing on the application. So in the end, like we came up with like kind of 5 different things that he kind of suggests, and I also suggest too. We talk about that. So the most basic thing is that there's some free stuff out there, all right, and we should try to get and use them, all right. For example, like all those collections and the things from Biohackers, for example, like the bicystron junction that I mentioned a few slides ago. Those things are on the process of developing that they should be freely available soon, right? So at the most basic level, we should be familiar with this kind of free stuff, the same way that we should have been familiar with Linux and Unix and programming language when it came out, like decades ago, right? And we should think about like the application, the new kind of application that is significant to us, but other big players might not think about, because like the research are so diverse all over the world, right? So there might be some applications that we can think about and we can lead. And you can partner with the 2 developers. Most of the big players in the US or also in China and in Europe, most of them are kind of busy making tools. They are like my research, making the big memory or like making the good oscillator, making like a logic gate, right? They have some kind of application in mind, but they are not so diverse, right? Because the research and the research that they have been seen, since they get educated in biology, right? So the things that they have seen are different from the things that we have seen, right? And also another thing is that we could think about these 2 and 3, number 2 and number 3, as kind of like idea and test-based engine. So most of the 2 developers care about that tool being used, right? If you make a new tool, right? If you're a hammer or like a program computer, you want a lot of people to use them, right? And those are actually the problem that this guy is having right now. Every time that I go to the meeting, people are going to talk about like, how are we going to try this kind of tool in the different contexts, all right? Most people just like, oh, we prove a principle, and that's it, right? How are we going to use it in different contexts? So if we can if we can function like a test bed, if we can use the tool that already exists in a slightly different condition and show that it's actually reusable or it needs some kind of specific modification, then that could be the strength that we have too. And in the end, we also want to be part of the global community. For example, join the competitions or other kinds of things. Right? And so now let's go back to my goals. Right? I'm not sure if you get excited or not, but this is like the short-term goals. Right? And to go from the short-term goal to a long-term goal, then like we need to figure out like the way that we work together in the middle range, right? So one suggestion that I got over the past years, my advisor is that all this new technology, usually it's not start from the PI, my advisor, it starts from the student. You thought like you might think like it's like some professor very smart think about making this technology. No, most of the time it's like the student who like, why don't we try this? Why don't we try that? And they communicate with one another across the boundary of the country or the lab, right? Because they're curious. They're like, oh, let's try this, try that. Everything is possible, right? And another thing is that they are the one who actually touch the wet stuff, right, of the lab. So any kind of movement, any kind of initiation that you want to start, I don't know, start from us, as a student. We can start talking about it now. So right now, like I and some of my friends here, like Piogan and like Maprang and Guang, and we try to study. So basically, like the past week and like today also, we try to think about maybe there are all different kind of different applications that we already have in Thailand, or even just here, right? Different kind of applications that people over there might not ever think about at all, right? And try to match that with all the tools that has been developed over the past decades. So for example, over the past few days, try to write up this kind of thing, So I just showed you a few examples, but I have more.